some of you already have actually. But let me just okay, so the question of course was something like this. We are talking about SU2 by Z SU2. And we were asking what group is this? Okay. Now there are several levels at which you can answer this question. The first question is, let's figure out what ZSU2 is. So the center of SU2 is of course all elements of SU2 which commute with every element, right? Obviously the identity has to belong to the center, so the center is obviously a non-empty set. In general, ZG, so the definition would be Z of G is all elements of Z which belongs to capital G such that for all small g, in capital G, ZG equals GZ. So that's what a center is. And we had claimed, I think I've not really proven this, but it was a perhaps assignment, that ZG actually is not just a subset, it's a subgroup, and not only that, it's a normal subgroup of G, which is why this quotienting operation leads to a group. By the way, I should perhaps clarify this. I have actually kept on saying that when you do G by N, that's the quotient group, of course. But I have perhaps been guilty of also saying that this quotienting operation makes sense only when N is a normal subgroup. Strictly speaking, that's not true. You can always do this for any group G. You can always do G by H, which by definition would be the set of all cosets GH. Okay, that will be a set. And is that set useful? The answer is often yes. For many of our applications, the cosets of a particular subgroup will really be very, very important and useful. Okay. However, it's only when H is a normal subgroup does this actually lead to a group. So G by H in general is not a group. G by N, where N is a normal subgroup, is a group. And that's where you get the quotient group from. So if you want to get a group out of this process, then of course what you are quotienting by, this has to be basically a normal subgroup. However, you can always quotient by any subgroup and end up with this kind of structure, which is a set now. It's not a group in general because if you multiply two elements of this group, you do not get another element of the group. Okay, not two elements of this set, then you don't get another element of this set. Okay, in general, that happens only when H is a normal subgroup, as we have shown. Okay, but cosets with respect to a particular subgroup are often very important, even very important in physical applications. When you study spontaneous symmetry breaking, for example, the cosets are really the mathematical structures which are involved there. And if so basically you have a symmetry group which breaks into a smaller symmetry group, and the cosets with respect to that smaller symmetry group are actually the relevant physical sectors in that problem, in some sense. We are going to hopefully describe that near the end of this course in detail, how that works out. But so quotienting is an important thing even if H were not a normal subgroup. And it's loosely what you are really saying is something like this. When you are in a sense, what you're doing when you're quotienting is you're saying all elements of capital H are for some purpose the same. Okay, so you don't count them as different elements, you just lump them together in a single element. And that, coupled with the group multiplication law, essentially tells you that every element of a coset is going to be treated as a single element. Okay, so for some physical purposes, all elements in a coset will behave like the same element, or they behave equivalently. And so basically when you're quotienting, what you're really saying is, okay, I am going to treat as distinct elements only those which have distinct physical features or distinct mathematical features, if you're doing mathematics. That's a very loose statement, we will see this actually used in physical applications, and then you will find exactly why that thing is being said. Okay, having said that, let's come back to this particular case where Z is a normal subgroup. So this is really a quotient group. So the first step would be to find Z. Okay. So what exactly is this Z of SU2? Now there are theorems. There's in fact a very important lemma that we are going to talk about, which is going to play a stellar role in the theory of representations, which is going to come next, which actually tells you what the answer is almost with no work at all. But remember that it comes with no work at all simply because you've already done the hard work in proving the lemma. Okay. Right now, since we do not know that particular lemma, which I'm not even going to mention right now, or not going to its name or describe right now, the only way we can find out the center of SU2 is by essentially hard work. But that hard work is actually not very hard, because you should remember that we already know that all elements of SU2 are of this form, right? Is there any problem with that, this statement? Everybody remembers this, right? This was one of the first thing that we discussed in the first discussion. Not the first thing, but in the first discussion class, we discussed this. That every element of SU2 can be labeled by two complex numbers, alpha and beta, whose mod squares add up to 1. And the four elements are given by alpha, alpha star, beta, and minus beta star, respectively. Okay? Everybody remembers this, I hope. Okay. The silence might signify that I have been disconnected, or it might signify that everybody has understood this. Okay, maybe what you should do is elect somebody among yourselves to keep on saying yes or no at periodic times, so that I know that at least I am still here. Someone? Am I here?
Yes, Subir.
Yes, sir. Yes, sir.
So at least what you do is what you should do is for each class at least elect one person. It doesn't have to be the same person every time, so that he or she at least lets me know that I am still there by answering such inane, stupid questions which everybody knows that there is no answer for. But anyway, fine. So this is something which everybody understands, I hope. So this is an arbitrary element of SU2. So we are looking for those elements of SU2 which are in the center. So let's claim that this element x, y, x star minus y star is in the center of SU2. What that will do is that if you multiply this by any of these elements, alpha, beta, alpha star minus beta star, what you should get is an element which is actually which is the same as the result you get if you were to swap the two matrices. So let's just multiply this out. And in fact, you don't even have to multiply all four elements. You know that SU2 is closed under matrix multiplication, right? So if you just find the top two, the top row, the bottom row fills itself up. The top row, of course, has these elements, x alpha. Okay, just check whether I'm doing my algebra right, which I'm notoriously bad at doing. Minus y beta star. That's what goes up here. Okay. And then you get x beta plus y alpha star. I hope I've got it right. I'm not even bothering to write down what these two elements are, but you should check that this element is the conjugate of this one, and this element is negative of the conjugate of this one. Right? So this is what you get when you multiply it in this order. What you get when you multiply in the reverse order, you can of course multiply again, but you don't really have to multiply, right? If you want to figure out what happens when you switch the two, all you have to do is replace x by alpha and y by beta, and that's it. So what you are insisting when you're saying that the matrices commute is that this element x alpha minus y beta star must be the same as what? Okay, now I want an answer. Same as what? Yes?
X alpha minus beta y star.
Okay, let's see. You're going to change the x to alpha, right? That's, after all, it doesn't really matter which one is x, which one is y. The formula is general. So what you can always say is, if I were to interchange these two matrices, x and alpha get interchanged and y and beta gets interchanged. So this should be alpha x minus, okay, y. So y, what will come in? Beta will come in. And as you rightly pointed out, beta, so you get beta y star. Okay, so this is what you must have, which means this cancels out. And note, this has to be correct. For what? For this has to work for what values of beta or beta star?
All values of beta and beta star.
For all values of beta, right? This has to be correct for all values of beta. That's perfect. Okay. By the way, let's check what happens with this first. The other equation. The other equation tells you x beta plus y alpha star. X is replaced by alpha, beta by y, plus y goes to beta here. Then alpha star becomes x star. Okay. So what is the first equation telling you? What is it telling you about y? That's the important question. If minus y beta star has to be minus beta y star for all beta, remember, not just for real beta or imaginary beta, for all beta, what does this tell you?
Y should be 0.
Yeah, this is really trivial. It says that y has to be 0. If you want to check that, I want to check why that is true. Okay, I think I made a mistake here. Yeah, I made a mistake here. The equation was y beta star equals beta y star. Yeah, that was the equation. Now, of course, to check whether it's right or wrong, all you have to do is, let's say, take a purely real beta. That will tell you something about about the connection between the complex and pure and imaginary parts, real and imaginary parts. Take a purely imaginary beta. Again, you will get a result, and that will immediately tell you that y has to be 0. That's the only way you can have y beta star equal to beta y star. Of course, if that is true, then this term drops out. And what does this tell you about x? Then, remember, again, this has to be true for all beta. What does this tell you about x?
Can be any.
This tells you that
Any
x is
real.
real, right? X is equal to x star. That's all. But now what you know is this matrix that you are talking about, the matrix which commutes with all SU2 matrices, has to be some real number x here, 0 here, minus 0 star here, and x star here, which of course is x. But now what? Now comes the last part. What is x?
It's plus or minus 1.
Remember, x mod square plus y mod square has to be 1. And x being real, this simply translates to x square equal to 1. Of course, you can see that from the thing here. So x square equals 1 implies x is plus minus 1. So basically, these are the two matrices which together make up the center of the group SU2. The only SU2 matrices which commute with all SU2 matrices are the identity and the negative identity. That's it. Now, you all obviously know, at least you should immediately be able to tell that this forms a group, these two, the identity and minus identity together forms a group. Okay, I'm using the wrong notation. There's a set of the identity and minus identity. And the operation here, of course, is matrix multiplication. So if you multiply these two, you know that they form a group. And what we already know from what we have studied is that there's only one possible multiplication table you can have here. And here, of course, you can just verify that that's true. And this is really the same as the group Z2. Remember, when I say this is the same as the group Z2, I mean it's isomorphic to the group Z2. There's a one-to-one homomorphism. And here the one-to-one homomorphism is simple. You just Z2
Sir, I think you got disconnected. Sir?
Okay, am I audible again?
Yes, sir.
Okay, so let me just resume the presentation. So when was I disconnected? That is, did everybody see this?
No, so that when you were writing the thing in the box on the left.
This one, this isomorphism. Okay, that's sort of trivial. All I was saying is we are going to actually say, we can actually say Z of SU2, the center of SU2, is a set containing the identity and negative identity, and it's a group under matrix multiplication. But And we can also say that this is isomorphic to the group Z2, but we will very often not say that. We'll just say the center is Z2. And this is the language that you have to sort of get used to. Okay. Very often we will make some rather outlandish statement like some set, which is some group which is obviously made out of entirely different elements, is actually another group with an entirely different set of elements. But that simply means that the two groups are isomorphic and we don't bother distinguishing between isomorphic groups. So instead of saying SU2 by center of SU2, I'm saying SU2 by Z2. The question that I have for you is, can you identify this group? You should know what the answer to this is, that this is isomorphic to some well-known group.
SO3.
That is this.
This is SO3. And how do you show that? Yeah.
So I think in the SU2 manifold, you just join the antipodal point.
Hmm.
So then you get this SO3 and Z2.
And that's exactly the opposite of what you really do. SO3 manifold is one where you join antipodal points. SU2 manifold has no antipodal point identification that way.
No,
So
I'm
you
saying
mean
SU2 by Z2, doing that.
okay? You mean in
Quotient
the SU2 in the S3?
No, SU2 by Z2, the quotienting what we do. So
Yeah, but antipodal points. What do you mean by antipodal points here? SU2, remember, we worked out that SU2 essentially is, as a set, is the same as S3. Right? That was the group
Right.
manifold.
Yes.
And that, of course, is what you can see here in what I wrote down. Two complex numbers, which means four real numbers whose squares add up to 1. That's every element of SU2 is related to the set of four real numbers whose squares add up to 1. And this is a one-to-one correspondence, right? Give me any set of four real numbers whose squares add up to 1. I can give you a SU2 matrix and vice versa. And this is obviously one-to-one. You change any one of the, of course, you can't change any one of the four numbers because their squares have to add up to 1. But if you change the numbers, you're going to get a different matrix. And also, if you change the matrix, you get a different set of numbers. So there's a one-to-one identification between SU2 and S3. And of course, S3 being a sphere, you can always say, let us identify antipodal points on a sphere. But are you doing that when you're doing SU2 and Z2?
So when we are quotienting SU2 by Z2,
Are you identifying antipodal points? So antipodal points would mean X, Y, Z, W is 1 point on S3. Remember, these are not points on a sphere in 3 dimensions. This is a 3-dimensional sphere which is embedded in 4 dimensions. Okay. What you are claiming is what you do is this: minus X, minus Y, minus Z, minus W. Is that what you are really doing?
yes, because identifying the antipodal points, so
Which essentially means that in terms of the alpha beta complex numbers, alpha beta is being identified with
minus alpha
minus beta. And that's perfect. That's exactly what you do, because there are 2 elements in your center. Okay, I keep on making this mistake. I keep on. Okay, there are 2 elements in your center, I and minus I. Okay. And that means that every coset, no matter what matrix, SU2 matrix you take, let's say U is an SU2 matrix. The coset actually has 2 elements, U and minus U. Of course, if you go by the S3 representation, the 3-dimensional sphere version, then U is a point on the surface of the sphere, minus U is a point which is exactly in the opposite, antipodally opposite point. So you're right, what you're doing is you are treating those 2 points as the same point. But how do you end up with that statement that gives you SO3?
Because you show in an earlier class that if we match the two antipodal points of an and S3 manifold, then
That was an entirely different manifold.
well,
The antipodal point matching that I showed was basically a ball in 3 dimensions. And if you match the antipodal points on the surface, if you identify them as the same point, you end up with SO3. But that's
right.
an entirely different manifold altogether. Here you are saying take S3 and match and map antipodal points as the same point. Showing that that is equivalent to this is really not trivial. So don't confuse the two.
Okay.
But I did show you one thing, right? I don't remember whether I did show this. I think I showed this, which is how there is a homomorphism between SU2 and SO3. Did I show you that?
Yes, sir. In an earlier class.
Yeah. And the kernel of that homomorphism happens to be Z2, which you can easily check. So basically, SU2 quotiented by Z2 is isomorphic to SO3, is a simple consequence of the isomorphism theorem, the second isomorphism theorem. Although you don't really need that, because all you have to, if you remember what we did there, we showed the homomorphism basically by starting with this construction. You take this sigma dot r, form u sigma dot r u dagger, that gives you sigma dot r prime. I hope everybody remembers this. And this r prime is basically some rotation acting on r. We showed all that. So basically from every SU2 matrix, you can correspondingly find an SO3 matrix. And that this is a homomorphism is easy to show, that if you replace u by u1, u2, where u1 gives rise to r1 as a rotation, u2 gives rise to r2 as a rotation, it's trivial to show that u1, u2 gives rise to r1, r2. So that's a homomorphism. That is onto takes a bit more work, not very much. But it's not one-to-one because it's easy to see that u and minus u both will give you the same result. So the homomorphism, where the identity, that is, if u sigma dot r u dagger is the same as sigma dot r, you can easily show that that can happen only if u is either identity or minus identity. Exactly the same kernel. The kernel is the same as the center. In fact, it's pretty trivial to show that the kernel is exactly the same as the center here. And so the second isomorphism theorem would also have told you that this is SO3. Depends on how much information you want to put in. But when I said that problem, I really wanted to make sure that everybody can identify the center properly. And then at least say the quotient group is made out of matrices of the form u minus u, where u is an SU2 matrix. And by the way, just to ensure that you don't overcount, you have to ensure that if you label u, you don't label minus u. How to do that is something I will let you figure out. So are there any further confusions about this?
Sir, does that corollary of the second isomorphism theorem help us to directly arrive at this?
Not really, because I would say the second isomorphism theorem is more directly applicable here. That corollary actually would tell you that, okay, you want to figure out the set of all inner automorphisms of SU3, the SU2. That's actually difficult. That is the same as the group SO3 is actually something you can more easily show by using this result already, which is already there. You can, of course, identify the set of all inner automorphisms of SU2 to be SO3. Then you are done. But that's really not that easy. I would say we would usually use that result to arrive at this. That result is very important, but not for the purpose of this particular problem. Okay, anything further? What about the problems that were there in the class test? They were sort of very simple. But did everybody get, is there any confusion about that?
So, is it possible to have like some more time for the class test? And this class test was easy, but the class test we'd have in the
we have an
future.
hour usually.
But similar format as this.
The similar format is this, but you will have more time. More time depending on whether the questions require more time.
Okay, sir.
The questions that, look, these questions were trivial. You could have solved most of them in 2-3 minutes. Most of them.
Yes, sir.
So now, of course, I may not really be a great judge about how long it takes you to solve a problem. You are only the best judge of that. But I would say if it takes me 2 minutes to solve a problem, 5 minutes is decent. Of course, I have the advantage of already knowing the stuff beforehand, which is the big advantage, definitely. And setting the questions. Of course, if somebody said I set an arbitrary question in group theory, I might even take more time. I would say for those questions, 5 minutes is enough, and say 5 minutes for the uploading. Now, this time VLearn had an issue, and people are trying to sort of solve that. In fact, I think it's more or less solved by now. There was an issue with the connection. And I will try to explore whether Google Classroom can be used, which will sort of help us get rid of this problem with VLearn being slow at times. Okay, so are there any further questions, or can we jump to the next topic?
So just in follow-up to that, I think it would be, I don't know how open you are to this, but it would be better if we didn't have to scan separately for each question, because that's sort of resulting in a lot of wastage of time.
Yeah, but scanning separately for each question, basically what I might try to think of another way of getting around this, let's see. But I want the answers in time. And I shouldn't tell you, I have to tell you why I want that.
Yes, sir. So in that case, you could like the question expiring at that point of time and moving on to the next question is okay. So you can just scan and upload at the end.
And well, even that doesn't always work. Let's see. Let's we try to figure out some way around that. I will try to ensure that you can scan and upload at the end, but yeah, let's see. Not all questions are really amenable to that. I'll try to set questions accordingly. Let's see. Okay. Anything further? Okay, if not, let me also point out the obvious to you. This week you have not had any new lectures uploaded. Okay, there was one at the very beginning of the week. That's because of two reasons. One is I have myself been way too busy with 2 other courses which I'm handling right now. But more importantly, because I wanted to give you some time to assimilate the stuff that is already up. The abstract part of the group theory course, at least the first half of the abstract part is nearly over. There is just one more lecture in that, which should be up maybe by tomorrow morning. Depends on how silent the time I get, because there's a lot of noise in my vicinity right now, so I can only wait until the evening for recordings. But anyway, that will be on direct and semi-direct product of groups. Okay, so that is the last part of the abstract or abstract group theory part, which mathematicians usually study. There's a lot more to abstract group theory than just this much. Of course, we have not even scratched the surface of that, but that's the part that will be most important for us to work with. Okay. The next part will be representation theory, the theory of group representations, which is also abstract maths really, but which is more tuned towards us physicists because the motivation behind studying that is entirely rooted in physics. And that is, of course, what we are going to use directly in physics. Okay? So that's what is going to come. But before I go there, let me just take this opportunity to introduce you to another kind of application of groups, which we will not cover in great detail in this course, but which is very interesting and useful. And in fact, some of the things that we study here, like say, what good are cosets really in physical applications, those things can be seen in effect here. And I will give you a reference to a wonderful lecture, or not a lecture, a wonderful article on this. Is Mermin, the same Mermin of Ashcroft and Mermin, whom I'm sure you have read. This is okay. This is what is exactly okay. I don't really remember the exact name. It was something like this. Of course, this is not what I'm going to talk about in the rest of the course, for the simple reason this requires things called algebraic topology. Okay, and algebraic topology is not a part of this course. It's definitely a part of the mathematical phase course. Who is teaching that, by the way? The advanced mathematical physics course? Is it this semester or the previous semester? I've forgotten that.
So the previous semester it was
Who taught
taken
that?
by Panigray, sir.
Okay. Did you hear anything about this? Not about this, but about algebraic topology in the course? Anybody who did that course, that is. Of course, that's an elective. Okay, nobody's sort of owning up. I hope I'm still connected.
You are, sir.
Okay. Fine. So this is one topic which we are going to discuss, not today, but in one of these discussion classes, because I want to give you a flavor of what else group theory is good for. Okay, you might see that in the title there's no mention of group theory, right? It says topological theory. However, the way in which group theory enters into it is something called the fundamental group of a topological manifold. That's a big
Hmm.
name, but it essentially means something very simple. And if you read Mermin's article, you will find it's described in very, very lucid language. There's some math in it. Of course, there's a lot of math in it, but the math is in later halves. And even if you don't understand all the maths, in fact, it shouldn't be difficult to understand all the maths, but at least the way in which a group emerges in this and where the group becomes important in deciding what kind of defects you can at all have in various condensed matter systems, that is a very, very nice application of group theory. So we are going to talk about that. I'm just giving you some time. I would urge all of you to read this article, at least the beginning of it. You should be able to find it on the net. If you can't, I will give you a link to that, which is available already. Okay. Since you have not heard of, I am assuming you have not heard of algebraic topology yet. That is, yes or no? Well,
No,
can
sir.
anybody just tell me what was taught in the mathematical phase course? Come on, somebody must have done that course. Nobody did that course? Yeah. Okay. Anyway, so one of these weeks in the Friday class, I'm going to talk about this particular topic. After, of course, covering all the doubts, etc., that you have. Okay, let me just utilize the rest of the time today in giving you a quick overview of why we talk about representations all the time. That is, what is so good about representations. I'm not going to tell you about representation theory here because that's a whole set of lectures. I'm going to just talk about a physical problem and try, sort of outline how you would use group theory there, and on the way you will see where representations come in. The physical problem I will talk about, there are many, of course, that's really what this course is about, how to use group theory in physical problems. So the particular physical problem I'm going to talk about today, I'm not going to solve it in detail today. That's again a topic which we are going to cover after we study representation theory proper. But let me just indicate what kind of system it will be that we are going to talk about. Let's say we have a square molecule. This of course is a fictitious molecule, some molecule which is entirely in the shape of a square with identical atoms of mass m at each corner. Now, one very important question about such a molecule is what kind of motions such a molecule can have. In other words, all of you know this, right? You have done the theory of small oscillations, right? And normal modes.
Yes, sir.
So here, if you are going to study, okay, so this fictitious molecule, the square molecule, it has 4 atoms at 4 corners, identical atoms. And let's just assume that it can only move in the plane of the paper right now. So that really gives you 4 times 2, 8 degrees of freedom, right? Is that okay? So if you want to talk about small vibrations, what you will end up with ultimately is a situation like this. You have an equation where, let's say, this xi is the displacement of each molecule, some numbers, 8 numbers which describe the configuration of this molecule, the displacement of this molecule from this equilibrium position. And that's going to be something like sum over j, kij, xij. Plus, of course, higher order terms, nonlinear terms. When you say small oscillations, you ignore those nonlinear terms. Everybody is with me so far? And typically you put in a minus sign here, simply because you want to relate these kijs to the spring constants which you usually get in standard linear force laws. Okay? So basically, okay, in general, what you will have is a situation like this. If at 4 different masses, you would have mi xi I double dot equal to minus sum over kij xij plus higher order terms. Of course, there are no constant terms on the right hand side. Of course, is the force. There are no constants on the right hand side. There is terms independent of the xi's, because we are assuming that xi equal to 0. Xi1, xi2, xi3 all equal to 0 means that the molecule is in equilibrium. That's the equilibrium. So xi equals 0 signifies the equilibrium positions of the molecules. Non-zero xi's tell you that you have moved away, and if xi is small, then the higher order terms are going to be small. Okay, so this is of course pretty straightforward, and you all know this. And this, of course, you also know that you can obviously write this as a matrix M times a vector xi. Okay, I'm just using xi as a column vector here, an 8 by 1 column vector equals minus k xi, right? Where k is of course a matrix made out of the k11, k12, etc. elements. And you also know this kij is symmetric. Kij is really nothing but the second mixed derivative del xi del xj of the potential, and so kij and kji are equal is sort of trivial from the mass. Okay, and if you want to talk, how do you then come to the normal modes from here? Okay, the equation is m xi double dot equal to minus k xi, where m is this matrix with elements, ij element given by mi delta ij. That is a scalar matrix sorry, not a scalar matrix, a diagonal matrix with elements M1, M2, M3, M4 down the diagonal. Okay, how do you solve this to get the normal modes? That's a question. I'm addressing it to you. Tell
So
me,
we
how do you
find the
get normal modes
eigenvalues.
out of this?
We'll
Yeah.
find the eigenvalues and eigenvectors of the matrix.
You find the eigenvalues and eigenvectors of what?
Of well, first you put that xi to be some xi naught into e to the power I omega t something. The omegas are frequencies, and then you put this into the xi dot.
You are saying that you do this.
Yes, something like this, and then
Now, what is the
xi dot.
justification for that? Why do I do something like that?
So e to the power I omega t is just well, that's it's like a blend.
It's like a what? No, look. When you say xi is xi naught into the I omega t, what you're claiming, of course, if the I omega t is not the real displacement, everybody knows that. The real
Yeah,
displacement is the real part of this. Sorry, I can't really hear you very clearly.
So just that, well, that is just the oscillation. E to the power I omega t is what? Cos omega t, and then the
Yeah,
side
when
sine.
you take the real part, you get a cos omega t plus phi. Phi coming from the fact that xi 0 might also have phase terms. Right? My xi 0 may not be real. So when you take the real part, you get xi 0 cos omega t plus phi, or component by component, something like that. But my question is, how do you even know that you can do this? The tricky part here is when you are saying xi equals xi 0 to the I omega t, you are saying that every component, every one of xi 1, xi 2, xi 3, right down to xi 8 are oscillating together with the same frequency. How do you know that that's even possible? Now, this has nothing to do with group theory. This has something to do with very basic physics. What, of course, the calculation that you do in this problem is finding out eigenvalues and eigenfunctions, ultimately. However, if you just think about this normal mode problem simply as an eigenvalue problem, then you are missing the basic physics behind it. Why is it an eigenvalue problem in the first place? And what does it really mean when you say you're going over to normal coordinates?
Is it something center of mass?
The center of mass is not really very relevant here. It's actually important in part of the theory of the vibrations, but the real issue is something else. The real issue is it so happens that you should be able to change your variables to a new set of variables by doing some kind of linear transformation such that the coupled equations that you have here, where xi1 double dot is related to k, xi1, xi2, xi3, all of them, if you just could go over to a new set of coordinates in which this equation becomes decoupled. That is, from xi you go to some new eta, and the equations for eta basically look like eta double dot is something times eta. Eta 1 double dot is something times eta 1, eta 2 double dot is something times eta 2, and so on. And these somethings are constants which depend on the kij's and mi's, but ultimately what you have done is you have managed to decouple the equations. So these are decoupled things are actually the normal modes, and each of them oscillate on their own with their own specific frequency. Now when you are saying that, what you are actually saying is, suppose I manage to set up initial conditions in such a way that only one of the normal oscillations where excited, all the others stayed 0. Then of course what will happen is eta 1, eta 2, eta 3, all of there will be no eta 2, eta 3, eta 4, only eta 1 will be oscillating. But xi 1, xi 2, xi 3, these are linear combinations of eta 1, eta 2, eta 3. So if only eta 1 is non-zero and all the others are 0, then xi 1, xi 2, xi 3 will all be oscillating with the same frequency. So the very fact that you are making a statement like this, that xi is xi 0 to the I omega t, presupposes that you can actually decouple the equations, which is basically where the mass is, and write down independent oscillator equations. And it's possible to set up a situation such that only one of those oscillators gets excited, so that in terms of the original coordinates, all of them are going to oscillate with exactly the same frequency as that particular normal mode. All that is already put in when you make this ansatz. This ansatz is not arbitrary. You cannot just start by saying, okay, let's assume this and hence I get a solution. The physical meaning behind this ansatz is you can decouple the oscillators and you can have individual oscillator-like behavior. I'm pretty sure you all knew this, right? Okay, and after you put this in, then it becomes sort of trivial. If xi is of this form, then xi double dot is minus omega square times xi. So the equation essentially ends up becoming m omega square m xi equals k xi. This is not exactly an eigenvalue equation yet, right? You can claim that it is by saying, okay, omega, this is the same as omega square xi is m inverse k xi, right? And therefore, omega m inverse k is a matrix, an 8 by 8 matrix, whose eigenvalues are the normal modes, the normal frequencies, and so on, or actually squares of the normal frequencies. But can anybody see why we don't really do that? We actually don't try to find the eigen frequencies of m inverse k. Can anybody tell me why? What you do is something more complicated. What you do is you write omega square m xi. You start with this. Then you do something rather strange. What you do is write it like this. And then go over and you now call this thing eta, and you end up with omega square eta is k bar eta, and now you find out the eigenvalues for this matrix k bar, where k bar is m to the minus half k m to the minus half. By the way, what am I really doing here when I say I'm forming this m to the half zeta and calling that eta and so on? What I'm really doing is really very, very simple. It's almost trivial. Yes? You have seen this happen, right? Haven't you done this? If the answer is a no, then tell me it's a no.
Sir, I think it's a no. I mean, it's not clear what you're saying we've seen.
So suppose I had a set of equations like this: m1x1 double dot equal to minus k11x1 minus k12x2, and m2 x2 double dot equals minus k21x1 minus k22x2. I'm just using two variables here, just to keep things simple. How do you proceed here? If you wrote down the equations directly, you'll get omega square m1 x1, sorry, not x1 double dot, because that's actually what that is. So this is the equation which really says omega square m xi equals k xi, right? That's just this equation written out in full. Now this is not an eigenvalue equation, right?
Yes, sir.
So, sorry, I couldn't hear you.
I said yes, sir.
Okay, but you can treat this. First of all, you can treat this as an eigenvalue equation in this form. You can say this is omega square xi is m inverse k xi. Okay, and since M is a scalar, that is a diagonal matrix with masses on the diagonals, it's easy to say that M inverse can be formed. So there is no problem with M inverse. So this is a perfectly good equation to write down, and you can find out M inverse k's eigenvalues and say that okay, those eigenvalues are what omega square are. Okay. However, what I'm claiming is instead of doing that, you actually try this and find out eigenvalues for this matrix k bar, which is given by m to the minus half k m to the minus half. Which again, m to the minus half is what is the matrix raised to the power minus half? Well, in this case, it's pretty trivial. All you do is take all the masses, take their square roots, and form the reciprocal. So it's a diagonal. It's again a diagonal because the matrix is diagonal. It's really just this matrix. M3 and so on. So you just multiply k on the left by this, on the right by this, and you have a new matrix k bar. While I'm pretty sure this derivation that omega square eta is k bar eta should be sort of obvious, right? The question is the motivation. The fact that omega square m eta equals k eta. Oh, sorry. Shit. And this is the same as omega square xi equals m inverse k xi is sort of absolutely obvious. It is the same as omega square eta is k bar eta, where eta is m to the half xi and k bar is m to the minus half k m to the minus half. That's slightly non-trivial, but it's pretty easy to see that if you put this into this equation, you will get exactly that thing back.
So, but for
and
m
there is
to
no
the power
problem
of
with the
half,
invertibility of m.
so for m to the power of half and minus half to be well defined, we need it to be a diagonal matrix any case. And
no, you don't need it to be diagonal matrix, but the fact that you have a diagonal matrix makes it even easier.
so why do we choose to do the latter over the former? So if we can, like, if we
Yeah,
have a
so
diagonal,
that's the question. Why don't you? What does this matrix k bar have, which m inverse k does not have? Which is what makes k bar a better thing to use. For practical reasons as well as from the mathematical point of view. From a purely practical point of view also, K bar is much easier to diagonalize than M inverse K. Why is that? Okay, what's the most important feature of K? This matrix K? I've already mentioned that. Yes?
It's symmetric.
Yeah, it's symmetric. Is M inverse K symmetric? M is symmetric. Of course, it's a diagonal matrix. K is symmetric. M inverse is also symmetric. But the product of two symmetric matrices, is it a symmetric matrix?
They have to commute.
They have to commute, and they don't in general commute. Remember, M is not a scalar matrix. If M had been a scalar matrix, that is, all the diagonal elements are the same, then there would be no issue. Then, by the way, M would have, if of course they commute, if M and K commute, then you should realize that K bar and M inverse K are exactly the same. Right? You can just move the M to the minus half across the K then and get M to the minus 1K. Is that okay? But in general, they don't commute. As a result, M inverse K is not a symmetric matrix. Now, the problem with not having a symmetric matrix is, first of all, it's not even guaranteed that a symmetric matrix can be completely diagonalized. And more importantly, most of the algorithms that we have for, say, calculating the eigenvalues and eigenfunctions, they work much, much faster on symmetric matrices than on general matrices. Okay? So that is precisely why you would want to move over to a symmetric matrix first. And this is what makes K bar a symmetric matrix, which guarantees that it can be diagonalized. Of course, after the fact, you can also claim that since you have been able to find out K bar, which is a symmetric matrix, and because K bar can be diagonalized, hence M inverse K can also be diagonalized, because this is nothing but the M inverse K diagonalization equation. Then you can prove after the fact. But it's K bar which actually is the one which is guaranteed to be diagonalizable because it's symmetric. Right? If you take the transpose of K bar, what happens? K gets transposed, but these two swap. But they're the same, right? Even if they swap, it makes no difference. Remember, M is a symmetric matrix, so its transpose is the same. So is M minus to the bar, M to the minus half. They're all symmetric matrices. But the important thing is AB transpose, of course, is B transpose A transpose, so it just turns out to be BA. So that is why M inverse K in general is not symmetric. So it's a symmetric matrix that you are really looking for. By the way, this is what this has nothing to do with group theory at all. This is a elementary physics. This is the first step that you do, which essentially means instead of using your x coordinates, what you use is root m times x as weighted coordinates. So for every component, you take root m times that as the actual coordinate, x bar or eta or whatever you call it. And that ends up giving you a symmetric matrix to diagonalize, even if you start with different masses. Now, you may not have come across this in your problems for one very simple reason. Very often the problems you may have done are simple and they're the ones with all the masses being equal. Right? And in that case, of course, it doesn't really matter whether you take root m into x or not. It's just a matter of uniform scaling then. And also then, of course, your capital M matrix commutes with K because it's just a scalar matrix. So these two approaches give you the same results. But the general method in the calculation is you have to go over to this matrix K bar, which is m to the minus half K, m to the minus half, and then diagonalize that. Okay, having said that, this again has nothing to do with group theory, and it's rather irrelevant for our discussion right now, because remember, our molecule has 4 atoms. They form a square and they have 4 identical atoms, so all the masses are equal anyway. So for us, frankly, this was just an academic discussion. For this particular result, you don't need to worry about the distinction between the two. So you can just simply say m omega square Xi. Because M, all the masses being equal means multiplication by the mass matrix is the same as just multiplication by the single number M is K Xi. So your spring constant matrix, my audio is cutting out quite a bit. Okay. Is that the case for everybody? Okay, so do one thing. Give me 5 minutes. I will just switch to a different room. Is this any better?
Yes.
Okay, I hope this should be better here. Anyway, let's okay, so what I was trying to say is our particular problem is one in which all the molecules, all the atoms in the molecule have the same mass. So for them at least, it doesn't really matter whether you worry about this capital M matrix or not, because ultimately it doesn't, what you are going to end up with is this one relation where small m is the value of for the common masses, and you end up with this expression. And perhaps because you have only handled problems in which all the masses were identical, you did not have to worry about the distinction between the two situations that I talked about. In our problem, of course, we have a symmetric molecule. All the masses are the same, at least for the time being. The general theory is important because we would also like to see exactly what happens when you change, say, one or two of the masses. Isotopic, say you change the molecule to another molecule with isotopes replacing the original atoms. So how would the vibrations of the molecule be affected by isotopic shifts? This is actually a very, very important physical tool which allows us to learn a lot about the actual nature of the molecule itself, and group theory plays a huge role in trying to sort of tell us what will be the possibilities. But let's come back to the direct point. I'm going to quickly go over the steps that people would take to solve this problem using group theory. Some of these steps most of these steps will not be explained today. I'm not going to explain exactly what the mathematics is behind those steps. What I'm going to tell you is what is done, and hopefully that will tell you exactly why we are interested in abstract group theoretical properties. Like, say, the representations, which are also, after all, abstract mathematical properties of groups, but which most abstract group theory courses don't cover because it's more useful for physical applications like ours. Okay, so first of all, let's talk about what the scenario is like. This square molecule of ours it can of course oscillate and distort and form various shapes as time goes by, and these atoms will keep on oscillating. Now you're solving this equation m omega square xi equals k xi. The k is a symmetric matrix, so you have 8 eigenvalues. So 8 normal frequencies. Okay. Now, among the 8 normal frequencies or the 8 eigenvalues, I can easily tell you that there are few which vanish. In fact, exactly 3 of them vanish. That I can tell you just on the basis of physical experience with the system. There are 2 modes of motion in which, if we were to displace, say, all the atoms equally in the same direction, what happens? The entire molecule translates, and that of course is a possible motion, and that kind of motion will have no restoring force whatsoever, right? Because the molecule as a whole has shifted, there is no distortion in the molecule, no restoring force, which would mean that this would have absolutely no tendency to come back, zero frequency. There's another zero frequency mode, which is that yes. What is the other zero frequency mode? Am I still here? I think so. It seems that I'm still here.
All the points moving out in opposite directions. So like,
You mean what? You mean like this?
yeah,
That would definitely not be a zero frequency mode, right? If in a molecule all the atoms moved out like this, there would be substantial restoring forces. And we'll try to get everything back again.
yes.
That actually happens to be a normal mode, by the way. That's one of those normal modes which are easy to identify even without any group theory. But that's not a zero frequency mode. What other zero frequency mode are there? Or is there? There's exactly one more zero frequency mode. Remember, we are only considering planar motion of this molecule in a plane.
So what about the motion when like the left side is moving towards the right and the right side is moving towards the left?
Left side is moving towards, so you mean like this?
Yes, something like that.
Do you think that this will be a zero frequency motion? No restoring force?
No, now I think about it.
In fact, that actually is also another normal mode. In this case, I've taken a very simple example, so the normal modes can be sort of identified with, most of them can be identified just by thought. In fact, the one which you have come up with is another normal mode of oscillation.
So what about translation about like perpendicularly?
About?
Like
About the perpendicular axis, you mean?
Yes, sir.
Yeah, but that's something we are not even considering here. I'm saying
okay.
Let's assume that the square can only move in the plane. That's just for simplicity.
Yes, sir.
Within that, we have two translational motions. That is, are rotations allowed? Tell me.
Since it's a planar motion, I don't think so the rotations are allowed. or rotation in about the normal to the plane.
Exactly, rotations above the normal to the plane, that is rotation in the plane. That of course is allowed. For example, you can have motion like this. Then the whole thing turns, right? But does not get distorted. As a result, there is no restoring force again. Okay? So there are two translational modes which have zero frequency, and in this case, one rotational mode. So three zero frequency modes. These are also Eigen frequencies, of course. The point is, if you take all the x's to reflect either translations along the x-axis or translations along the y-axis, or you take these particular precise combinations of x's, then you get, basically you see when k acts on xi, you get 0. That means for them the omega is 0. So these are also Eigen frequencies, but zero frequency. So there are 5 non-trivial frequencies to be found out in addition to the 3 zero frequency modes. These are the 5 vibrational modes. I'm sure you have done this, right? You have done this even when, say, statistical mechanics, for example, when you figured out vibrational degrees of freedom and so on. Maybe not in this language, but you definitely have done this somewhere. Anyway, coming back to this, how do you find out the Eigen frequencies? The answer is diagonalize the matrix, right? So you have this 8 by 8 matrix which you need to diagonalize. Now, diagonalizing an 8 by 8 matrix by hand is not really very, very simple. Okay? Now, you might say, nowadays we don't need to do that. You can always go to a computer and ask us to diagonalize this, right? We have wonderfully nice diagonalization routines available in almost every programming language. Just fit the matrix to your computer, you get the answer. While that is perfectly true, you have to realize that this gives you absolutely no insight as to what is really happening. You just get some numbers and you don't understand. For example, 2 frequencies come out to be the same. That's just an observation. You don't even know whether that's really an accident or whether there's something deeper behind that. Okay. So just finding out the frequencies, if that was your entire goal, then I would have said, okay, forget group theory, just use computers. It will, the hard work is done by the computers, you get your answers. End of story. The trouble is, in almost all cases, physics is not just about getting the numbers, but also about understanding the numbers. And that understanding a computer calculation will not give you. I'm not saying computer calculations are bad. All I'm saying is just computer calculations cannot tell you anything real about physics. You have to supplement that with the physics inputs. And that is an important point. Now, of course, you might say 8 by 8, I can still do by hand. You can, actually, if you work hard enough. But if you have a bigger molecule, say the Buckminster Fullerene C60, that's in 3 dimensions, that's a 180 coordinate. So you have to diagonalize the 180 by 180 matrix. Even if you could do that by a computer, but doing that by a computer would give you 180 frequencies which you have no understanding about. So this is where group theory comes in very handy. The symmetries which the square molecule has, they form a group, and this group actually tells you a lot about the possible normal modes. Okay? Now, you might also say that, okay, I can always simplify the problem by making some approximations and then I can handle them by hand. While that is also true, the real problem would be that you can not be sure that what you are seeing, if you see some general features after solving something by hand or by a computer, after making some approximations, then you can no longer be sure whether what you're seeing is due to the approximations you have made or because of the general features of the system. Okay? So this is where group theory comes in. Group theory simplifies the analysis of this problem. It allows you to calculate the Eigen modes much more easily. By the way, can you tell me one thing? Which is easier to calculate? Given the eigenvalues, finding the eigenvectors, or given the eigenvectors, finding the eigenvalues? Yes, that's a very simple question, straightforward question. If I give you an eigenvector for a matrix and ask you to find its eigenvalue, how would you do that?
We multiply it with the matrix and
yeah. That's all you do. You just multiply it with the matrix, and that immediately gives you the eigenvalue, right? Given the eigenvalue, finding out the eigenvector still takes a lot of work. Of course, what makes life harder is that nobody gives you eigenvalues for free, right? In general, you're given a matrix. The only way you can find out the eigenvectors is first solve the characteristic equation, find the eigenvalues, and then from that find the eigenvectors. That's the usual route, right? Actually, what group theory helps you to do is identify the eigenvectors. Well, not always, but at least tell you, at least do something like this. At least tell you that the eigenvectors might be either tell you that these are the eigenvectors of this matrix, or it tells you that the eigenvectors can be sort of reduced to a combination of, say, 2 vectors or 3 vectors. Okay? Which means that instead of having to solve an 8 by 8 eigenvalue problem, now you have to solve only a 2 by 2 eigenvalue problem or a 3 by 3 eigenvalue problem, which of course is much more tractable. How it does that, I'm not telling you now. I'm only telling you this is what you gain out of using a group theoretical analysis of the problem. Okay? Right? So did you understand what the gain is? I'm not saying did you understand how you do that, because that's what we are going to spend lectures on when we talk about molecular vibrations and stuff like that. Yes, any confusion so far? Okay, so not only that, group theory actually also tells you what is the most general possible form for K given that you have these symmetries in your system. Okay, so you can do a most general analysis without even bothering about specifics of a particular molecule, and then you can always, given a particular molecule, you can see whether you are getting the most general form. If you are not getting the most general form, you're getting something simpler, then you would look further and see that there has to be some reason, some other special feature of the molecule which is making it even simpler. So that sort of guides your analysis process a lot. Okay. Now, let me just tell you one more thing today, because I can't simply finish the whole thing today anyway, and I'm not even telling you much. I'm just telling you what can be done, not what is exactly done. But let me just tell you one important thing. Given this molecule which is moving around, how would you describe its displaced configuration? There are several ways, but one obvious way would be to say, okay, this atom moves here, let's say, and this atom moves somewhere. This atom moves maybe here, and this atom moves here. So all you need to do is give, this is of course not a normal mode. I'm not talking of normal modes here. I'm just saying this is a general motion. Where to describe the general motion, what you will need is you will need to sort of set up some coordinate system. And in this case, the basic idea would be, let's just take these 8 eigenvectors, or 8 vectors, not eigenvectors, sorry. E6, E7. These are basis vectors in your space of displacements. Your space of displacements is actually 8-dimensional. And there's nothing very strange about having high dimensions. It's just you need 8 numbers to describe this. You have an 8-dimensional space, and every atom sort of this, how much is the displacement of this atom? You write that as x1 E1 plus x2 E2. But x1, x2 are just the x and y components of, or horizontal or vertical components of the displacement of this atom. That's for the first atom. Then you have x3 E3 and so on. Right? So basically this will give a complete description of the possible motions. Right? So now you have an 8-dimensional space formed by E1, E2, E3, E4, E5, E6, E7, E8, and their linear combinations. Okay, now the question is, if I were to carry out the symmetry operations of the square on this, what will happen to the matrix element, to these basis vectors? Now that you have an 8-dimensional vector space spanned by these 8 vectors, what will happen to these 8 vectors when I carry out the symmetry operation? Of course, that depends on which symmetry operation you're talking about. Which is the simplest symmetry operation of the square? Yes?
The identity.
Identity, which of course does the simplest possible things. E1 goes to E1, E2 goes to E2, and so on. And the matrix for that, once you know how the basis vectors move, you can figure out what the matrices are. But here the matrix is trivial. It's just the 8 by 8 identity matrix, right? That's trivial. But let's say,
what is this? So what is this matrix you're talking about?
This is a linear. That's okay. Now that I have this 8-dimensional vector space which describes all possible displacements of the atoms, there's a vector space, right? On the vector space, we can do linear transformations.
Yes.
In fact, the symmetry operations of a square produces linear transformations on this vector space as well.
Okay, so it's a linear transformation of the symmetry of the
linear transformations which are connected to the symmetries of the square. And I could have talked of any linear transformation, but we are really interested in the linear transformations which correspond to symmetries of the square. And one of them is the identity, and that of course keeps all the basis vectors intact. And the matrix representation for that, matrix which represents the identity transformation, is of course the identity matrix. Not a big deal. That's the simplest thing. Is it okay?
Yes, sir.
Now another symmetry, very simple. Say reflection in the midline. Now can anybody tell me what happens to E1 under this?
So basically, E1 goes to E7.
Good. E1 becomes E7.
E7 goes to E1.
E7 goes to E1, but more importantly, what happens to E2? Okay, not more importantly, we need all of them. What happens to E2?
E8.
It becomes minus E8. E3?
E5.
E5. Okay, you've got the idea. I hope everybody understands this. Okay, let me just do one more, just to make sure that everybody has understood this. This operation that we perhaps named C or something. Okay, this doesn't really look right. This should be a straight line going through the two corners of the square. So there's a diagonal reflection in that. Okay, quick question. What is E1 under this? Yeah.
Sir, I think E1 will remain as E1.
No, E1 will not remain E1. It will reflect in this diagonal.
It becomes
okay, so
E2 or E4.
it becomes
E1 becomes
E2.
E2, right? And E2 becomes E1. Right? It's a 45-degree line. So x-axis becomes y, y becomes x. What happens to E3?
It becomes E8.
it becomes E8, right? Because this atom moves here on the reflection, and of course, because you're reflecting along a diagonal line, this horizontal vector becomes vertical. Now, I'm sure you have all realized that by this approach, you can find out what each of the symmetry operations, the 8 symmetry operations of the square, does on the 8 matrices, 8 basis vectors. Okay. Unfortunately, there's a coincidence here which was really not intended. You have 8 symmetry operations of the square. You also have 8 basis vectors here, but those two 8s are unrelated 8s. Okay. It just happens to be a coincidence that they match. But in general, all the symmetry operations of whatever object you're talking about, they should act on your basis vectors describing the displacements. And as a result, what you will get are 8 matrices, in this case 8 or mod G matrices. Each matrix essentially telling you what happens to the displacements under the symmetry operations, right? Okay. Now, let me just ask you one thing. Suppose I know the matrix corresponding to A, which A is one of those symmetry operations, B is another symmetry operation. A and B are actually, in our original notation, was a horizontal reflection and a vertical reflection. Can anybody tell me what AB is? If A is a reflection in this line and B is a reflection in this line, this is A, this is B. What is AB? We have discussed this before several times.
Diagonal
There
reflection.
is just a rotation.
Rotation through how much?
The rotation through 180 degrees.
Exactly, it's a rotation through 180 degrees, which we call G when we label them. But doesn't matter. This is a 180 degree rotation. This is just a result, special case of the result that if you have two lines which are at an angle theta and if you reflect successively in them, you end up with a rotation of 2 theta. So these are 90 at 90 degrees, you get a 180 degree rotation. What is very important and what is really where all this comes from is the matrix corresponding to A. Let's call that D of A. The matrix corresponding to B. Let's call that D of B. How is that related to D of G? Yes? What's the connection between DA times DB and DG? How are they related to each other?
Sir, I think it should be homomorphism if I'm not wrong.
Well, even if you never heard the word homomorphism, you should know that if A is represented by DA, a matrix, B is represented by DB, a matrix, the way these matrix representations are made, I'm not talking of representation in group theory, I'm just talking of representations of linear transformations by matrices. All you would immediately get is this has to be correct. DADB is DG, which actually leads to the fact that these matrices are homomorphic to the set of operations. Okay. So the abstract operations or the geometrical operations that you were doing, rotations and reflections, the matrices that you have written down are homomorphic to them. Now, matrices are actually much more concrete objects. They're easier to do mathematics with than abstract group operations. So this is one of the reasons why we look for representations like this. We will make representations more formal in the lectures, but representation really essentially means this. You want to represent abstract operations of a group by either linear operators acting on a vector space or its more concrete form, matrices acting on column vectors. Okay. And the important thing is, this is an approach which is going to respect the group operations, the group structure. DADB has to be equal to DG because AB is G. Okay. Now, as a result, what you have is instead of having to deal with abstract group elements, you're dealing with concrete matrices, which is an advantage in its own right. But the only problem is these are 8 by 8 matrices, which are big matrices, right? Would be nice if you could break them up into smaller matrices, which is again where group theory comes in. It tells you that you can actually go to a new basis in which most of these matrices will become as diagonal as possible. What that means, we are going to, you have to take this loose statement for the time being. I'm saying try to make them all as diagonal as possible. When I say all as diagonal as possible, exactly what I mean, you will see. You will see when we talk about this more formally. You can't really diagonalize all of them together. These matrices don't all commute, right? Because you remember your group is a non-abelian group. As a result, the matrices which represent them would not all commute, right? In general. So, not all. You may have, in fact, by the way, you may have matrices which respect group structure and still commute. But right now, in most cases, because the group is not abelian, the matrices which represent group elements would also typically not commute with each other. And because they don't commute with each other, you cannot diagonalize all of them together. What you can do is try to get them as close to diagonal as possible, which means basically something like this. You should be able to go to a situation which looks like this. I'm not going to show you the details of that right now, but what I'm going to tell you is something like this. Suppose you may end up with a situation which looks like this. Okay, what I mean here is that these are the only non-zero elements of your matrix. So out of the, of course, if I had managed to diagonalize all of them, the structure would have been simply like this, right? Non-zero elements only on the diagonal, zero everywhere else. But because we do not have commuting matrices, we cannot possibly go to a basis where all of them become diagonal. But what I can do, and this is what group theory helps us to do, is find a new basis in which all of them will end up becoming very close to diagonal, or at least take a form like this, which is called a block diagonal form. And there's not about one matrix. All the 8 matrices will take this form. Okay, this is what you can easily. Okay, clear? If it's not clear, say so. Okay, I'm just making a statement here. So please don't ask me why this will happen. But have you understood what will happen? Yes? Yes, no. Am I at all here? Yeah, I am here. It seems so. It of course might be possible that you may be wondering that I'm going to repeat it all over again and make it even more difficult if you say no. But even if that's the case, tell me. Are you at all following what I'm saying?
Yes, sir. I mean, it's sort of trivial, I guess.
It's not trivial. I'm not even saying that I've explained why this can happen. Okay, you will soon see. You will see once we go through the theory of representations and in particular irreducible representations, you will easily see why this structure has to occur in general. But what I'm trying to point out here is this will happen. Question is, do you understand that this can be done? That's what I'm saying. I'm not asking you to understand why. I'm asking you, have you understood what we are trying to achieve here? Diagonal
Yes,
matrices
sir.
would be the easiest to handle, but matrices which do not commute cannot be simultaneously diagonalized. So you cannot go to a new basis where all the matrices are diagonal at the same time. If that happened, your problem would have been very, very trivial. That doesn't happen in general. So just give me a couple of minutes.
I just wanted to say that we've seen such, such structures in some sense. Like, okay, this we've seen these matrices in action in some sense. So you're muted.
Sorry, I had to attend to a call. So you were saying something. Somebody was saying something.
I said that we've seen such representations in some sense. We've seen such matrices, and we've seen
You've seen
how.
such matrices. Examples of that, say, rotation matrices, for example. You must
Yes,
have seen
I
such
mean the
examples. The
Rx,
point is,
Ry, Rz. We've seen such. So
sorry, yeah,
the rotation about the x-axis and the rotation about the y-axis, and we've seen
yeah, but
how.
matrices usually, usual representations will not come out in this block diagonal form. But you can always choose your basis in such a way that they will come to as close to diagonal as possible. And the great thing then is this, essentially what, so this is where the ultimate thing comes in. Group theory helps you to find out how to do this, okay, how to change the basis. And once you do that, the really funny thing is this will tell you, for example, it will tell you that, okay, there's a basis vector which transforms just by picking up this factor under the, of course, this factor will be different for different group operations, but this particular basis vector here, say the fifth basis vector in this way we have written down, will just pick up a multiplying factor no matter whether you apply A on it, B on it, C on it, D on it, and so on. And that actually tells you that this fifth basis vector will correspond to an eigenvector of your matrix K. Why? We are going to come to that later. But this is what you're really doing. You're saying that, okay, here you have 8 basis vectors. 4 of them, in this particular example, 4 of them correspond to just diagonal elements. And these 4 are definitely going to correspond to eigenvectors of your matrix K. Remember, the matrix K has nothing to do with these matrices. The matrix K is simply a force constant matrix. The only important thing is that matrix K actually commutes with all of these symmetry operations. Again, details later, but the result is this. These 8 vectors, out of the 8 vectors, these 4 will definitely give you the eigenvalues directly, because these are going to be eigenvectors of K. And once you know the eigenvectors of K, you immediately know what the eigenvalues are, right? You can just multiply by K that eigenvector, you can get the multiplying factor. On the other hand, it also tells you that this and this, the first and the third, the first row here and the first row here, the actual eigenvectors of K will be combinations of these 2 vectors and these 2 vectors only. At least, sorry, there are 8 eigenvectors of K. 4 of them are just these 4 immediately identified by the calculation. You don't have to do anything else. Okay. But the moment you have, say, 2 identical irreps sitting on the diagonals, you would say this and this together give you 1 eigenspace. So now the problem gets reduced to a 2 by 2 matrix calculation. So 4 of them come out immediately. For the other 4, you have to solve 2 by 2 matrix problems. Now, this is the power of group theory. This is what group theory will tell you how to do. Again, I have not told you anything about how group theory tells you this or given you justifications for this. I'm just telling you why would you want to study representation in the first place. Representation theory is what allows you to do this kind of thing, not only for this particular problem, but for most problems where you have symmetries. It essentially boils down to finding out representations, representing matrices which represent your system, and then trying to break them up into these small blocks which are called irreducible pieces or irreducible representations. And once you know all the irreps of a particular group, which actually is what we are going to devote considerable time to over the next half of the course. After I talk about the direct and the semi-direct product, which ends the discussion on the abstract part of group theory, then we will have at least 8 or 10 lectures essentially on how to find out irreps. Of course, it will have to be built up as to what exactly irreps are and exactly what kind of machinery you use. And that will give us the tools that we can then apply to any physical problem, and that will tell us how to find out, say the eigenvalues here much more easily than it would be possible otherwise. It just doesn't end here. For example, it will also tell you things like which of these eigenvalues will be active under, say, will help you to absorb infrared radiation, for example, or which ones will be Raman active. So essentially, in quantum mechanics, that's what you're trying to find out is which matrix elements are zero and which ones are not zero. And that information is encoded in the irreps. So because people ask me why would we study representation theory at all, I thought of giving you a preview of that. This is not representation theory. This is not the mathematics which you will need, but this is just a sort of trailer of why we are doing this kind of thing. Once you go through representation theory, what I've said here will become trivial, and then calculating these things will become much easier than it would be otherwise. So remember, you have started with a problem where you have to diagonalize an 8 by 8 matrix. But what we are saying is group theory will help you to reduce this problem to essentially finding out the special basis on which all these become block diagonal. There's a very standard machinery for doing that. That is a kind of algorithm which you fit the whole thing in and you get the result out that way. And once you have those basis vectors, they help you to reduce the problem of finding out the 8 Eigen frequencies to basically essentially trivial problem for 4 of them and solving 2 by 2 eigenvalue equations for the other 2. So having said that, so this is basically the power of group theory and in this particular application. But the same sort of shows up everywhere, whenever you use group theory, at least in this context. There are many other ways of using group theory in physics, but this is one of the most important ones. Okay, any further questions? Okay, I'm not even sure whether people are awake or they've all fallen asleep. Somebody is awake, right? No, I'm not very sure. Okay, is the connection very bad today? Because I'm seeing several people leave and rejoin over and over again. That usually happens when the network goes very bad. I'm not even sure whether anybody is still in.
Yes, sir, we are here.
A few of you are here. Anyway, fine. This was not a concrete class in the sense that I have not taught you any real physics or real mathematics today, but that will come in the lectures. Okay. So all I want to emphasize is the next half of the course is going to be new to most of you, because even those of you who have done abstract group theory would not have seen group representation theory done unless you have done a representation theory course from maths, and even that would focus on essentially different topics than ours. So what I'm trying to emphasize is this particular part of the course is really why we are doing the whole thing at all, and then we are going to apply this to physical problems. So the tough part is yet to come, but this is essentially why you should have to sort of go through the tough part. Okay, if you have any questions, you can ask me, or if not, we can just call it a day today.
I think we can call it a day.
Okay, I think everybody has had enough. Right, anyway, okay.
Thank you, sir.
Yeah, thank you for letting. Why are you thanking me for letting you go? I should actually stop recording before I say such things.